Having seen how every year we multiply the principal by 1.12 so that over a period of 3 years we multiply by 1.12 3 times, and after t years we will have multiplied by 1.12 t times, and saying that we have 1.12 to the t times our original principal at the end of t years, we can look at the principal function as follows. Principal as a function of time is simply equal to $10,000 times 1.12 to the t. Here's our principal function. The $10,000 out here is our initial quantity. The 1.12 is what we call the growth factor. It's the factor by which we multiply the principal each year to get the principal a year later. At the beginning of the year, if we have principal P, we multiply it by 1.12 to get the principal at the end of the year. The 0.12, that's our 12%, and we call that our growth rate. Now, growth rate is not to be confused with average rate of change, or even average rate of growth, although we wouldn't use average rate of change. We wouldn't use the word change and growth in the same context. A growth rate is something we multiply by a quantity to get the change in quantity, whereas an average rate of change is a delta y over delta t or delta y over delta x type thing. So we don't want to make any confusion. We want to be sure we have two ideas of the word rate, essentially. Okay? In any case, these are the components of any exponential function. What we have here is an exponential function. We call it exponential because the variable t is in the exponent. So we have some initial quantity multiplied by a growth factor raised to the t power. That's what comprises an exponential function. And we can tell what the growth rate is by looking at the growth factor. The growth factor is just going to be 1 plus the growth rate, indicating, again, in this situation that we keep our original principal, that's where the 1 comes from, and we add the interest, that's the 0.12. We keep our original quantity, whatever the quantity is, whether it's population, temperature, or whatever, and we add whatever the growth rate tells us to add. There's a recurrence relation involved with this situation, and here it is. It says that P of n plus 1 is 1.2 times P of n. What does this say? Well, if P of n stands for the principal at the end of n years, then Pn plus 1 is going to be the principal at the end of n plus 1 years. And how do we get the principal at the end of n plus 1 years if we know the principal at the end of n years? Well, that's a 1-year span, so we multiply by 1.12. To complete the model that we've just done, we say P of 0 is $10,000. At 0 years, we've got $10,000. Okay, this is a recurrence relation here and an initial condition here. From that, we again determine in general that P of n is 1.12 to the n times P naught. Whatever number goes here is going to be our growth factor, and if we go n years, we're going to have to apply that growth factor n times, and that's what we're going to end up with.